Okay, so welcome back. And it's my pleasure to introduce Nikolai Kiselev, who will speak about regularized micromagnetic model as related to magnetic singularities.
Yeah, thank you very much. As many other speakers, I also would like to start with acknowledgement to organizers to be here. Some speakers said that their talks are related to the end part of the title of this conference. I honestly, I would to believe that my talk related to the first part of this talk, and in particular to the progress. I hope so. So my talk is about magnetic singularities. So we are trying to kind of regularize a micromagnetic model with my colleagues in order to be able to include and describe this type of magnetic textures in our micromagnetic theory, which at the moment, and I will try to convince you with this, is problematic part. So my talk will be organized as following. So I will start with the short introduction to the chiral magnet, because that's the system which I keep in mind during the whole of this presentation. And then I will show you a couple of examples of magnetic solitons which include magnetic singularities in their texture. One of them is a so-called chiral bobber, and another one is a dipole string. So after that, so I use this previous part as the motivation to introduce our so-called S3 model and corresponding regularized LLG equation. Then I will provide you with some representative examples and compare the micromagnetic simulations which are based on the present micromagnetic theory and with the model which we suggest. And finally, I will provide you with outlook and conclusions. So the core part of my talk is basically content of these two papers, which we published with Vladislav Kuchkin. So he is the first author and basically the driving force of this project. So he is the main guy in this business. So the chiral magnet, so you already saw this functional in some other talks during this presentation. So I will talk about bulk crystals with Heisenberg isotropic Heisenberg exchange interaction, bulk type Zelensky-Mori interaction, which favor Bloch type modulations, Zeeman energy term, and the term which is responsible for demagnetizing energy field. So the typical example of these crystals is the white family of crystals with so-called B20 type crystal symmetry, which characterized by the absence of center of inversion, which together with a strong spin orbit coupling and this material give rise to Zelensky-Mori interaction. And here you see a couple of examples of this different compounds. So it's iron cobalt silicide, manganese silicide, iron germanium, and there are some other. So the typical temperature B field phase diagram look like this. So in the ground state, between 0 and up to Curie temperature, the ground state of the system is the helical spin spiral. So the homochiral modulations, which in principle at zero field form a multi-domain state where the K vector propagate in different directions, but applying not relatively weak magnetic field, we can saturate all these domains such that K vector is pointed along the field, magnetization is tilted towards this direction, and we effectively appear in a monodomain conical phase, which with further increasing of magnetic field continuously converge to a saturated ferromagnetic state. So these three phases occupy basically the whole phase diagram. However, if you cut a thin film from this material, you can get an extra phase composed of skirmions, which form a regular lattice. And so the mechanism behind this has been provided by Philippe Rybakov in 2013 with his colleague. He explained why in the case of thin films, skirmion strings, due to the so-called chiral surface twist, get energy to compete with other phases, helical, conical, and ferromagnetic phase. So later, together with Philip, we discovered and published a couple of papers related to another interesting solution. So we call it chiral bobber. And this statically stable configuration looks like a piece of skyrmion string, which starts from the free surface of your crystal and then ends somewhere inside the volume of your magnetic crystal with the magnetic singularity, also known as a Bloch point. So these objects are known in micromagnetic theory since ever, basically, because the seminal work by Feldkeller and Düring was published almost immediately after Brown introduced the micromagnetic theory. So they are known to be energetically higher in energy than any other continuous configuration, but nevertheless, they are a static solution with the finite energy. And from the static point of view, there is no problem with such singularities. So we identified the range of their existence. So we basically showed that everywhere where the conical phase is the ground state of the system, such object can coexist with the isolated skyrmion strings. And in a very small pocket here, they even can compete in energy with this isolated skyrmions. We even prove that this object can be experimentally observed, and with the help of people working in Institute of Microscopy and Spectroscopy with electrons in Forschungszentrum Jülich, we perform experiment and observe the configuration where skyrmion string, these two dots here, it's like two skyrmions of this type, and next to them you see a very weak spot, which is due to the presence of such configuration. So the natural question which arises after you get used with the existence of chiral bobbers in the nature is but whether we can stabilize something even more weird, where skyrmion string contains not just the one end but two ends like this. So this configuration are known in the literature as dipole strings. So that's basically the historically first name which they got in the literature. But they are also known under many different names like monopole, anti-monopole pair, magnetic globules, and similar to the terminology of liquid crystals, they're also often referred as torons. So I will use a name dipole string. So dipole strings in chiral magnets, it is well known that to stabilize them in the pure isotropic crystal would be possible only in the presence of either geometrical confinement, like for instance the nanowire here, some cylindrical sample domain comparable to the size of this object, or in the presence of other objects next to them. So in this case, you see an example of stable configuration where a bunch of these globules are sitting next to each other. But you also can find a stable solution with such object when they are located next to a skyrmion string, for instance. And so that they can have a different lengths, and these intermediate solutions are protected from each other by the finite energy barrier. But the problem is that we cannot call this configuration a soliton, because to be stable, it requires something next to it. And for a long time, we were puzzled whether and how we should modify our Hamiltonian to allow this configuration to be a really standalone, statically stable configuration. So, and this year, together with Vlad, we published a paper where we basically provide the answer to this question, and which is turned to be quite simple. So the only thing which you have to do is you have to add to your potential energy term the easy plane anisotropy. And another secret is that your external magnetic field should lie in this plane. So on this example, so the easy plane, the axis of the easy plane anisotropy is the x. So easy plane is zy plane, and magnetic field is pointed along z axis. So the phase diagram of the ground states of this system has been calculated before us. So here the easy planar anisotropy versus magnetic field, and here we have 4 different phases: helical, skyrmion lattice, conical, phase saturated state. So on top of that, we identify the range where such configuration exists as a stable solitonic solution as an excitation of the conical phase. As you can see, it's a relatively wide range of fields here. So, okay, so we have 2 type of magnetic solitons, chiral bobber. Okay, just quickly. So we also suggest how this solution can be experimentally identified. The problem is that in most of the chiral magnets, they have a very weak magnetocrystalline anisotropy. And none of them has easy plane anisotropy because they're cubic crystals. But we argue that shape anisotropy, due to the demagnetizing field, can play a role of this induced easy plane anisotropy. And if you cut your sample in the shape of plate and apply magnetic field alone in the plane of this plate, you already can satisfy the criteria for stability of such dipole strings. And here you see some examples of Lorentz transmission electron microscopy images or electron holography images, which we predict people should observe in the experiment. Okay, so we, again, I'm too fast probably. So since we have these 2 type of solitons, chiral bobber and dipole string, they contain these Bloch points. To really prove that they are solitons, we want to show that they are movable objects, so we can manipulate them like all other solitons. For instance, here, in this case, so we as usually rely on Landau-Lifshitz-Gilbert equation. Nowadays, the most common way to manipulate magnetic texture is the electric current. The standard way to introduce this in our Landau-Lifshitz-Gilbert equation is to add an extra torque, which is commonly written in form of Jean-Glie torque, which allows you to simulate the dynamics of magnetic solitons in the presence of electric current. So here you see the simulation for the pure 2-dimensional case so far, with solitons of a different topological charge. So all of them move with the constant velocity along straight trajectories. But the deflection angle with respect to direction of the current depends on the topological charge of this object. So for any topological soliton, we expect that its deflection angle depends on the sign of the topological charge. And only for those which have a 0 topological charge, the deflection angle is 0. So because of that, for any objects like dipole string or chiral bobber, which compose like a piece of skyrmion string with these Bloch singularities, we expect that they should move with along the straight trajectories with a certain deflection angle, which should be consistent with the deflection angle for ordinary skyrmions. But to solve this problem, perform these calculations is not straightforward because we have a natural obstacle for that. So the effective field which enter our LLG equation, even the Heisenberg exchange interaction, diverges in the center of this Bloch point. And we simply cannot apply this equation. Nevertheless, in the literature, you can find a lot of papers published with micromagnetic software of different kind, where people do use the simulations and do some analysis of this. But I have a strong suspicions that all that is a pure numerical artifact, and I will show you later why I believe so. So we have to get rid of this singularity here. So the most straightforward approach to do that, we have to introduce some other order parameter, which would allow the magnetization vector to shrink to 0 in the center of this point. That's the only way how we can satisfy the continuity of our order parameter in this case. However, by doing so, in principle, you can imagine many different ways to do that. But what we want to achieve at the end, we want to build a framework which would, from one point, allow us to describe the dynamics of such objects, which contains Bloch points. But on the other hand, we want this framework will be back compatible with everything what we know from the classical micromagnetics and now Lifshitz Gilbert equation. So we should be able to simulate both configurations with singularities and without them, and the results of simulations without singularities should fit what we know from the micromagnetics from the past, so to say. So we argue that the possible solution of that is to introduce the order parameter, which is a unit vector which is restricted not to S2 sphere, like in the classical micromagnetic, but a four-dimensional unit vector restricted to S3 sphere. So the first three components of this new vector are just the ordinary Cartesian component of our magnetization, and the fourth parameter you can consider it as a fictitious term or not observable quantity in terms of quantum mechanics, which is introduced exclusively to keep the constraint on our S3 sphere. So when you introduce this order parameter, okay, so now you have to rewrite your energy Hamiltonian. So we came to the conclusion that basically the most complicated part is the Heisenberg exchange interaction. So your Dirichlet term should be substituted by the following expression. So you have the gradient of all four components of your vector nu times the exchange stiffness, and plus the kind of anisotropy term, which put some penalties to the length of your magnetization, the real component of your magnetization vector. So the ratio between this new phenomenological parameter kappa, which defines how soft to some extent your magnetization, and the Heisenberg exchange stiffness provides the estimates to the size of the such a Bloch point. Interestingly, that all the other terms, in principle, you can just get by direct substituting of this nx and y and z with first three component of our new order parameter nu. So such approach immediately give you a solution where magnetization goes to zero in the center of such singularity. And in principle, this picture agrees with the quantum mechanical analysis of this problem, which has been provided in the paper of Vlad, which he published together with his colleagues from Luxembourg University, where they consider quantum Heisenberg model and prove that in this case, again, when you introduce such constraint on the system, which favored this hedgehog-like configuration, indeed magnetization tends to zero in the center of such singularity. So the next step, we have to rewrite and introduce a new version of our Landau-Lifshitz-Gilbert equation. And for that, we follow the simple geometrical analogy between these two spaces. So the dynamics of LLG in the classical case is basically the dynamics of the point on the surface of S2 sphere. So the velocity of this point is lying in the tangential plane to this surface. We can span this n dot with respect to two basis orthogonal vectors. The first one is typically called precession term, and the orthogonal to it, the second one is the damping term. So we want to do the same similar thing with our S3 sphere. It's just a schematic picture, of course. So in this case, the tangent space would be not R2, but R3 space. So because of that, we have to span our new dot vector on the basis of 3 orthogonal vectors. So the P, D, and H stands for precession, damping, and H, the higher order, let's say. So, and again, so we want our first term to be orthogonal to vector nu, to our effective field. But in 4 dimensions, not enough, so we have to use an extra ord of the in 4-dimensional space to satisfy the criteria of the orthogonality between P, nu, and beta. So on the next step, we want to have our damping term to be orthogonal again to nu, P, and beta. So it's easy to see that this linear combination satisfy this criteria. And finally, the last term is just orthogonal to nu, P, and D vectors. And all this, the cross product of these 4 vectors here, by that we mean the following operation. So the next step, we have to identify this coefficients in front of these ords. And to do that, I remind you that we want to build complete compatibility between our new LLG equation and the classical LLG equation. So if we set our new parameter, the force component of it to 0, so we converge to again to unit vector field on S2 sphere. So then the first and second terms should converge exactly to the same form as they are in the classical equation. So because of that, we immediately get the expression for the first and the second constants here. The third one, okay, let's formally put it as following. So far, we introduce an extra term, extra parameter epsilon times geomagnetic ratio here. And then the complete regularized version of LLG equation look as following. So the first 2 terms, they are, as in the classical equation, they are proportional to the first order term with respect to our effective field. But the third one is proportional to the second order term. So it does not have any analog in the case of classical LLG equation. So to avoid any kind of extra phenomena because at the moment we just want to achieve the proper description of the Bloch point behavior, and to get agreement with the classical micromagnetics, we have to have a one-to-one correspondence. So because of that, at the moment we set this epsilon parameter to 0 and exclude this term from consideration. So as soon as we do this, so then to add some extra torques in our LLG equation is more or less straightforward task. So here you see that the form of Zhang-Li torque in case of S3 model. And just for comparison here, I reproduced this expression for the classical S2 case. So now let's take a look how it works in practice. So Vlad implemented all this in the standard for micromagnetic simulation nowadays software, MuMax. And now every one of you can reproduce the results which I show you in the next slides when you come home and follow this link. Okay, so we start with the comparison between S2 model and S3 model, starting from the ordinary solution of a Skyrmion tube. So what we do here, we plot the longitudinal and the transversal with respect to the current vector velocity as a function of the strands of electric current, the electric current density. So in both cases, you see that solutions are fully agree. I don't show you any movie because it does not have a sense. So everything is trivial here. I will show a few later. So we have a complete agreement between the classical LLG and a new version. That's good. So we are on to some extent on the safe side. So now let's consider 2 other solutions which corresponds to a chiral bobber and dipole string. So again, on the left-hand side, you see the velocity dependence on the electric current density for S2 model for the classical micromagnetic. So these results you will get if you use any micromagnetic software. And on the right-hand side is the results for our S3 model. So in S3 model, everything is fine. The velocity follow the continuous dependence and converge to zero when electric current go to zero. But with S2 model, we have a lot of trouble here. So first of all, we observe some critical current below which this object don't move at all. But then when they start to move, they also do it in a weird way. So let's just take a look at a couple examples. So the dipole string, for instance, we start with, we use the same current and compare the dynamics of this object in two models. So in the classical micromagnetics, this dipole string is immediately pinned and does not move at all. In S3 model, it moves like with a constant velocity with the reasonable deflection angle, which coincide with the direction of the deflection angle for ordinary skyrmion string, which is reasonable. So if we increase the current density, okay, so now we can move the dipole string, okay. But if you look carefully, you probably can easily notice that it moves without any deflection. So it moves like topologically trivial object, which is okay. It's I don't know. There is no reasonable explanation for that. So it's a pure artifact. That's how I interpret this. But again, in S3 model, everything is consistent. It's keep moving with the same deflection angle, but slightly higher velocity as expected. The situation in chiral bobbers is even more weird. So we also have this critical current, which has no reasonable explanation. But then when we, so here I will consider two cases when we play with the mesh density. People often say that, okay, if you have some trouble with simulating Bloch points, just increase the mesh density, everything will be fine. Okay, let's try to do this. So we compare the results for relatively small mesh density in S2 and 3 models. So what we have. Okay, very interesting. So the chiral bobber, again, because it's a piece of a skyrmion string, it moves with the positive deflection angle, the same way as a dipole string, as the same way as a skyrmion string. But in S2 model, for some reason, it starts to move with another angle. But let's try to improve the mesh density. Let's increase it twice. Maybe this will help, okay? Okay, so S3 model shows the same behavior, we are happy, but that's what the hell is that? So it moves orthogonal, and believe me or not, but people really consider this as the physical effect. For me, it's a pure artifact. To conclude, so everything what you see here, we interpret as the numerical artifact and believe that proper behavior of the system is described by our model. Of course, the experimental proof will make the final statement on this in these debates. But before I conclude my talk, I want to show you some other examples related to even simpler case when we have just a soft magnetic nanowire with a certain length and the relatively wide diameter, large diameter, which favor appearance of head-to-head or tail-to-tail domain wall, which contains the magnetic singularity in the center. Yeah. So when your nanowire is very narrow and the diameter is comparable to the exchange length, so then you have a ordinary domain wall similar to what we saw in the first talk in this morning. But when your nanowire is relatively wide, so then the most energetically favorable configuration contains the Bloch point. So we take some parameters, plug them in micromagnetic simulation software, and try to see what happens. So we apply a really small magnetic field pointed along the axis, main axis of this nanowire, which make one of this domain more favorable than another, and which enforce the motion of this domain wall. And here you can see that the typical example of this motion, if you can say that it's a motion, it's just an oscillation. We apply a certain magnetic field, but the domain wall does not move, it just oscillates. And the frequency of this oscillation has nothing to do with none of this parameter, neither. So it has no physical explanation. So then, when you increase the strength of magnetic field, nothing happens. Then suddenly, with the low discretization mesh, your domain wall starts to move like a rocket with the almost kilometer per second velocity. But if you improve your simulations by introducing a dense mesh, then it suddenly either stop again or starts to move with the order small velocity, which again, it cannot be interpreted any other way than just a pure artifact. And if you do the same with our S3 model, then you will get at least a reasonable behavior where all the domain wall velocity follow the continuous law, converge to zero when magnetic field goes to zero, and all trajectories look like a straight line. So I shifted them just so they don't overlap, but you see that velocity basically with improving mesh density converge to a certain value. So to conclude my talk, so the proposed S3 model provides the physical consistent picture of the Bloch point dynamics, and also agree with our expectation for the dynamics of magnetic solitons like chiral bobber and dipole string. So I did not mention this in my talk, but besides the LLG equation, we also can derive by means of S3 model the equations for the collective coordinate in case of steady motion of our soliton, so-called Thiele equation. So we did this and compare the results of micromagnetic simulation with this semi-analytical approach, and they show a perfect agreement. Beside that, since we are able to derive this properly, so to say, our effective field without any divergence in the case of Bloch point, we also can improve the method of notched elastic band method calculation, which is used to estimate the energy barrier between a stable configuration. So we did this, and again, we improved the stability of this method, which before that showed the problem with convergence, which is again related to divergence of effective field near the Bloch points. So, and finally, a few words about this the last term here. So far we did not include it, but we because we always consider the configurations where we either already have a Bloch point or don't have it at all, like in case of Skyrmion string. But to be able to observe the transition between this configuration, it seems like this term is essential to be taken into account, and that's what we have to do. We have to set the epsilon to non-zero value when we want to do. But that's still is not finished project, so we cannot provide you with more information about the last term in this equation. So with this, I conclude my talk and want to thank all of you for your kind attention.
Thank you very much. Do we have questions?
Well, I mean, a natural question that arises: did you try to relax the unit length constraint and vector by considering some penalty away from the unit sphere? Did you try to incorporate some additional energy locally that pushes strongly pushes the vector?
What kind of order parameter you want me to take?
A vector in R3.
It's like Landau term, yeah.
Yeah, like Ginsburg-Landau regularization.
Yeah,
You try it?
Okay, yeah.
I mean,
I don't know. You might try, but I don't know.
Okay, first of all, it's great. I mean, I really
I can tell you what is the
like
practical
it.
problem with this approach, what you mentioned. How to introduce all this extra torques? We don't know.
You just put a normal, a torque normal to the surface of the sphere.
No, all these torques are derived in the assumption that
all
your
the other...
order parameter takes the
Yeah.
value on a certain manifold.
Yeah.
If it's just a ball with not exact constraint, like your n is less than unity, then you don't you cannot do much with that.
I think you can, but okay, maybe we can discuss a little more. Okay, I see what you're trying
So
to say.
that's
But
not the
you
only.
can make everything acting in a tangential direction. So, you know, even if you are not on the unit sphere, you could still be, you know, the other torque.
Why we are against of this approach when your order parameters in R3? So we don't want to go this direction because we know that from the quantum mechanical point of view that if you measure your spin can take a certain value, and it's whatever cannot be larger than that. It can be smaller than that because of let's not discuss which reason. Yes, Philippe also strongly against this approach, but again, we don't want to build
one approach.
Yeah, sure. I don't against you. Anybody can try this. I would be totally fine. But I suppose that you will end up with something inconsistent, just because you're trying to build your model on the order parameter, which is absolutely not physical. Magnetization vector cannot whatever go above a certain limit. Why we should build our model?
Project. You know, it's a method. You know, it means that you have to work better to make a method work. So, but okay. I mean, first of all, I really like your approach. But I was just wondering, it would be natural to try to compare with another.
It's absolutely natural, and people did this, but they did not like succeed much.
They didn't. So they tried it and it didn't work.
If they try and it didn't work, they did not publish it, so I don't know. But from my own experience,
Did you try?
No, we did not implement it that way as you suggest, but I foresee some trouble with that, with this approach.
Okay, well, okay,
I would be happy to discuss it.
Thank you. So my question is really about the same thing, but I want to emphasize I'm not against. I'm like it, but it is very intricate actually, because it supposes of existence of hidden variable.
Yes.
So we definitely do not know everything about our world, so could be something. But first of all, it would be interesting also to have here the column number 3 with Landau potential.
Yes.
This is my suggestion. And the second thing, your argument that spin physically cannot be bigger than something. So what is so it could be easily verified with practical simulation, if you wish, that if we using Landau potential, which is, let's say, explicitly 1 minus m squared squared. So despite your vector target space is R3, it goes beyond unity almost a little bit. It's practically, yeah. It in principle it can, but it never want to do it. So I mean, this is not too strong arguments against Landau-like potential. So this is my suggestions to at least have
So
this
you
third
basically
column.
argue, but it's the first and the second part of your comment, they are related. So as soon as we add a third column here with the Landau term, there you will be completely satisfied from the point of curiosity, at least, right? Yes, I agree. But it's not gonna be easy. I feel it. Let's do it. Yeah.
Thanks for your talk. Very interesting. I have a question from a physicist, not a mathematician. In the quantum case that was calculated previously, so you have this constellation of the spin, but spins are still there. So maybe is it due to the fact that you have a quantum superposition of plus and minus? So classically, it gives you something that is 0, but quantum mechanically, you still have something. So I think that the hidden variable that was evoked before, just the fact that instead of having some well-defined spin up, down, or left, right, we just have quantum superposition.
The quantum model of magnetism, of course, would be the first and the last most correct way. But with this model, we cannot go.
No, I agree. You cannot go, but maybe there is no hidden variable. Just that usually we consider the spin classically in micromagnetics, but if you consider them quantum mechanically, there is nothing that opposes that the average spin is 0. Even because you have up plus down, and that's all. Locally.
We do not so our model is to large extent is a phenomenological.
Yeah,
so
I agree.
Yeah. So the way you interpret this behavior of the system, why the order parameter, if it is take the value on S3, why it is so, we do not discuss so far. It's overcomplicated question. We are not ready to answer it yet. But superposition, of course, it's natural to assume that that's the key ingredient to understand why it is so, if it really works this way. There is temperature, yeah, and again, so we did not fully agree with Vlad on this point, so he is strongly against. I'm strongly in favor of temperature as an extra mechanism which contributes to that, but that's, yeah, exactly, yeah. Yeah, but the advantage of our approach that it also will work in the case when temperature goes to 0, contrary to, for instance, the such approach which are based on Landau-Lifshitz-Bloch equation or Landau-Lifshitz-Barrichtar equation. So there, all the fluctuation of magnetization I explain on term of the thermal fluctuations. And as soon the temperature goes to 0, you converge to a classical LLG equation, and then you again have a trouble with describing singularity. So our model is free of this restriction. It's still a thermal model. We don't have temperature, but temperature is somehow included in all these constants here. Yeah. With Hertel? No, of course not. No. His simulation is basically attempt to increase the discretization by order of magnitude, then embed everything in a small sphere, but put the kind of more diluted mesh outside of the sphere of the ball which contains the singularity. So he does atomistic inside the ball, but outside of this ball, it's a finite difference mesh again. And no, that's the complexity of the Hertel approximation of Hertel approach, because you have to move this ball together with your Bloch point when you do the simulations. But all the effects related to divergence of effective field, irrespective of how small is your mesh, they stay there. And only final experiment will prove who is correct and who is not. But I don't want to make a strong statement that everything what Hertel did is wrong.
Do we have other questions? Okay, if not, we thank again our last speaker,